Okay, now let's discuss the eelgrass situation with the same lens. And let's acknowledge, by the way, that eelgrass is a resilience feature for oysters, and oysters are a resilience feature for eelgrass. These habitats support each other. In this graph that begins in 1990, we're looking at eelgrass at 3 depths in the Great Bay proper, not the whole estuary, just the Great Bay. And the highest line there is the deepest grass. Just before this graph starts, in 1988 and 1989, the system was hit by a significant wasting disease event. But the system recovered to levels that were actually higher than 1986 before the event began. But since the mid-1990s, eelgrass is not demonstrating an ability to recover. Seagrass experts agree that reproduction from seeds is key to recovery, but seedlings require very good water clarity. They need a lot of light. Now, you'd love for this issue to be simple, but ecology doesn't work that way. It's complicated. For example, let's look at the issue of light for eelgrass. The fact that the deeper eelgrass in this figure shows more deterioration over time is an indicator that light may be an issue. So let's back up and review the main components that attenuate light for eelgrass. CDOM we've discussed before, and CDOM is natural. It comes from the breakdown of leaves and such. We know it's important. We don't have a lot of data on how it's changing over time, but some of the studies in the Gulf of Maine indicate that it is increasing because of increased precipitation. TSS stands for total suspended solids. We all agree that we have a lot of TSS in our system, and things have gotten worse in the past decades. Losing so much of our oyster and eelgrass habitat has probably only made the situation worse. Phytoplankton doesn't show any real trends. On the other hand, most of the stations that are further upriver, such as the oyster, lamprey, squamscot, show that levels are frequently fair rather than good, and less often levels are high enough to indicate poor water quality, meaning that we do see blooms in these tributaries. Seaweeds, we don't have a lot of data on seaweed, but what we have suggests that we've seen an increase in seaweeds since 1980. Epiphytes are things like algae that grow on the eelgrass blades. We don't have a lot of data on epiphyte changes over time. We need to look into that. The eelgrass research shows pretty clearly it does not reflect the complexity of our system to only focus on the components that attenuate the most light. They are all wrapped together, and management needs to look at reducing light attenuation where we can. For example, with regard to TSS, continuing to conserve land, riparian buffers, exploring the best shoreline erosion options will help to control TSS. With regard to phytoplankton, seaweed, and epiphytes, this does bring us back to nutrients because phytoplankton, and especially seaweed, outcompete eelgrass in high nutrient environments. Eelgrass actually doesn't need nutrients in the water column because it can get nutrients from the sediments through its roots, which seaweeds don't have. That's eelgrass's competitive advantage. Once nutrients reach a certain level, seaweed begins to take over, especially in a situation where you have warming waters, which we have. Other estuaries have shown that phytoplankton levels sometimes don't change as much in relation to increased loading because the phytoplankton get flushed out to the Atlantic in our case. However, for seaweeds, even a small increase in loading can lead to blooms, which then leads to decreases in eelgrass and sediment quality as the seaweed decomposes on the estuary floor. So for this reason, and other reasons that are discussed in the external advisor's statement, the 3 external advisors we consulted were unanimous in saying that further reductions in nutrient levels are warranted. They cite a comprehensive study from 2010 that looked at 62 estuaries in New England. That study concluded that seagrass systems begin to degrade when you have more than 14 tons of nitrogen per square mile of estuary per year. In 2016, our lowest nutrient loading year since we began looking at loading in 2003, we were at 33.7 tons of nitrogen per square mile per year. It's important to recognize the very significant investments made by the municipalities to reduce nutrients. We also recognize that we cannot achieve our nutrient reduction goals through point sources alone. Most of the loading comes from non-point sources. Also, Because our estuary has relatively little wetlands buffer, only 2.9% of the watershed, we are especially susceptible to land-based inputs of nutrients. And this emphasizes the importance of preserving our wetlands, thinking hard about riparian buffers, and decreasing impervious surfaces. As we said earlier, the goal here is to clarify the eelgrass and nutrient issue, but then to pivot to a broader perspective. And I want to close now by reminding you that we're dealing with multiple stressors, episodic, chronic, and multiple species, not just eelgrass and oysters, fish, lobsters, horseshoe crabs, amphipods, bacteria. This section of the report is about embracing a mindset that recognizes, in a context of dynamic change and stress, we need to seek ways to increase the number of resilience features in our ecosystems so that we can better recover and resist the stressors we face.